I like the control that happens in a lab, and the control is based on QA and QC, quality assurance and quality control. Basically, quality assurance is like a management overview of the quality in an organization or a program or a project, and it's the oversight, you know, the umbrella that covers the quality control, which are the specific activities during the data collection that produce the desired data quality. That makes sense? It's like a big program would be QA, and then the specific things you're doing under that are the QC. That's how I always look at it. But people will always sort of use those terms QA or QC kind of interchangeably. So this is just a few things that we go through from the sample collection level to the data report level that we do to mind the store on data quality. But just from a understanding toxicity standpoint, these are the things that we try to pay attention to when we're collecting samples all the way through to producing data reports, where we're trying to produce good data. First of all, there's also a laboratory certification program in California. It's ELAP, an Environmental Laboratory Accreditation Program. It used to be under, I think, the Department of Health, and now it's under the Water Board. And so they're expanding their definitions of laboratory certification using more of a national model to certify environmental laboratories in California. These aren't just toxicity laboratories or chemistry laboratories, water quality laboratories, like drinking water type analysis, and laboratories all through California. And so currently, Granite Canyon, our laboratory is certified, so I'm familiar with the process, and it's pretty arduous, and you got to jump through a lot of hoops to make sure you're certified in California. And so this certification program sort of handles a lot of these things, but the laboratory has to have these components in place in order to get recertified. So starting with sample collection, you know, anywhere from like again grab samples out in the field and bringing them back to the lab. You know, we have to use the correct sampling containers. You know, not to beat the pesticide horse to death, but pesticides are sort of the big deal right now in environmental, in ambient monitoring. And if you're collecting water samples in the field right now and pesticides are concerned, you want to use glass containers. You don't want to use plastic containers. Pyrethroids stick to plastic. And so you'll pour that water out and all the pyrethroids will stay inside the jar on the plastic. So we use glass containers for a lot of our stuff. No headspace, we keep them in darkness, we keep them in a specific temperature range, we mind our holding times. In a lot of cases we use special coolers for transport, to make sure things don't break along the way. This is a classic example of sediments that were shipped incorrectly, opening up your cooler and having lids popped off and mud all over the place. So it was a good time. And then keeping track of our refrigerator space, monitoring when samples go in, monitoring the refrigerator temperature every day. Taking that temperature every day to make sure the samples aren't warming up. With test preparation, getting ready to do our tests, we have our samples here that we get from the field. We want to make sure we have clean glassware. Whenever I have a new lab employee, they always start in the dish room, and for a piece of glass to go through our dishwashing process takes 4 days. So, we're doing acid soaks, solvent rinses, deionized water soaks, drying oven. I mean, it's clean when it comes out, and it's trace metal and organic clean. And you can't stress enough to a new employee how important that is, that they pay attention to every single beaker that's in their hand as it goes through the process. Because if you have a bunch of beakers on a shelf and a couple of them are dirty, then the animals in those beakers might not survive, and the animals in the other beakers do. Then you have variability among your replicates. That might happen in a control. It might mean that the test fails because it didn't meet test acceptability criteria because the glassware was dirty. So just simple things like housekeeping on the laboratory level are super important in making sure the data have good quality. Want to make sure we use the right glassware. Things like organism receiving, acclimation, and culture. Brian talked about getting organisms from suppliers or having cultures in-house. Those cultures in-house are monitored every day, fed, cleaned, renewed, and it's all written down. It's all record keeping day in and day out. Same with organisms that we receive. We have a specific protocol for every single organism that we receive from a supplier, the types of records we need to keep, and you have to be able to produce that stuff at any given moment for your certification process. This is much more important with a laboratory that's doing routine NPDES monitoring. That's not something we routinely do. We're certified for various other reasons, for various other projects, but a laboratory like Pacific EcoRisk or Nautilus in Southern California, these guys have these programs in place because when there are things like lawsuits or public protest or things like that, you want to be able to produce these records to demonstrate that the data were produced with high quality. Record keeping, ad nauseum. We have a pretty simple little shelf of logbooks, in purple and green, and it's fairly straightforward at our lab. We don't do a big volume of samples. We don't have a LIMS system, a laboratory information management system. It's all done by hand. Our logs are pretty simple. But in a larger laboratory, having a LIMS system or or some other computerized system that's going to manage your samples will do a lot of this work for you. We start with a chain of custody form. Every sample is received with a chain of custody form. This is important in the permit review process for reviewing the toxicity reports. We'll talk about this a little bit more tomorrow, but you can check things like holding time based on the sample data and collection times. You want to make sure that the correct organism's used. You want to make sure the correct test is used. All the contact information. This is sort of an abbreviated version of a COC, but it should have all the information on there. It's like an order form for what needs to happen in that laboratory. And every time the sample's relinquished and received by a party, like a sampling party, etc., there should be signatures involved to track that sample through space and time. And all of this stuff is kept in logs. We calibrate our instruments. We're not a very instrument-intensive field. We don't have gas chromatographs or mass specs. We basically have that little water quality instrument that Brian showed in the picture, and ours isn't even really that advanced. And so it's pretty simple, but these instruments need to be maintained and calibrated, and everything has to have a record. Our probes have names to them. They're all labeled for. And so, on our water quality data sheets, all of that information is collected so it can be tracked. Even things like our water, like all of the dilution waters that Brian talked about, we track our waters in the lab. We have water batches, they're logged, there's constituents measured in them, and records are kept of everything. So, within all of the protocols that Brian talked about, there's specific test conditions that are followed. Things like temperature, a lighting cycle, the size of the beaker you use, the volume of the water or the sediment in that beaker, dissolved oxygen, salinity conductivity. These are all things that are specific to the organism, and there's like a list of recommended and required things that have to happen for that test. And so some of these things you can actually see in toxicity reports. And so these are things that we can check to make sure that the test was run correctly. It's an example of a swamp method quality objective. And this is very similar to what's presented in the EPA protocols for each protocol. Each individual protocol has a list of things. And so you have like water chemistry, what measurements you should take at the beginning of the test versus the end of the test. Sample handling, you should be between 0 and 6 degrees. You should have a holding time of 36 hours. It's actually 48 for swamp. And then all the test conditions, temperature range that's allowed, light intensity, photo period, chamber size, all of these things recommended or required, like a laundry list of things that you need to do for the protocol. And again, good lab, certified lab, they're just going to automatically do these things. They have their method sort of set in stone and follow along with it. So I mentioned recommended test conditions versus required test conditions. So deviations from recommended test conditions may or may not invalidate a test result. And it depends on the degree of departure and the objective of the test. I mean, there's some situations, I've heard stories of laboratories where there will be many deviations of the recommended conditions, in which case, if as a permit reviewer, if you're looking at that, you're going, there's all of these recommended conditions that are just a little bit off, that might be a problem, if you're consistently seeing the recommended conditions, having deviations. So, but if it's once in a while, it's probably okay. Like we have situations, we have air conditioners that control room temperature for these tests. And sometimes you'll have an air conditioner go out of whack and the room gets a little too hot for a couple hours and then it goes back down. And then at the end of the test, the controls are all doing fine. The sample may or may not be toxic, but you wouldn't invalidate an entire test just because of that minor deviation from the recommended condition. But there are conditions that are also required, and you have to meet those for the test to be considered valid. Things like the minimum number of replicates. You can't, if it says you need 4, you can't use 3. So on. Test acceptability criteria. So this is one set of those required elements. And it's method specific, it's all related to the control. It's not related to anything that happens in the sample. It's only related to the control. And certain milestones that need to be met within that control for the test to be considered acceptable, like minimal survival or minimal growth, reproduction, fertilization. And this is the first thing that we look at when a test is terminated. And the crew's all trained to do this, as they're counting fish or whatever on that last day. And even during the test, they're looking at the control. If they're doing daily counts on fish, every day they're looking at those fish and they're saying, wow, we're starting to have a die-off in one replicate. And we know immediately when the test is considered a failure if it hasn't met a minimum TAC. But if we're doing a test like a sediment test where we can't count those organisms every day, we've run this test for 10 days, we've babysat it, we've fed it, we've made sure the aeration's good, and we're screening those sediments at the very end, and we're looking at our screen and we're counting how many animals are alive in the control. And if it hasn't met the test acceptability criteria, it's cause for like universal laboratory depression. Everybody's just, because we've spent 10 days, and fortunately it's sediments, there's a long holding time for sediments, and we can restart the test within a few days or a week, and we can do it again, but nobody likes doing that extra work. In the situation where there's an effluent or a water sample that has a short holding time, if you're going to retest that same water sample you have in the fridge, it's it's going to likely be beyond holding time. And in the case of an effluent, if you have to retest an effluent, usually retest with a fresh sample. Usually go out and collect a brand new sample from the treatment plant. In the case of an ambient sample, like I used the Salton Sea example, where the sample's 8 hours away, you're probably not going to drive back out there and collect a new sample. You might take the hit on the holding time and flag it within the database in order to have the data point. So an example of test acceptability criteria, I'm going to use the Cereodaphnia. Seridaphnia dubia. If you're doing an acute test, this is like a 48-hour or a 96-hour test, and you're just looking at the survival of the organisms, you have to have 90% or greater survival in the control treatment for the test to be valid. With a chronic test, this is the 7-day test, the average of 7 days, 6 to 8 day test. You have to have 80% or greater survival in the control. So there's 10 little cups, and each cup has one animal in it. And so eight of those animals have to live in your control for this to be considered acceptable. Of those surviving animals, they all have to produce 15 neonates, 15 babies over the course of the test. At least 15 per surviving animal. Now, the thing about Seridaphnia, this says per surviving female. The thing about Seridaphnia is, if your culture is in a good condition, they're all female. They're all girls. So, you have, so generally all 10 of them, when you start your test, will be female. And then of those 60% of those surviving females, greater than or equal to 60% of the surviving females have to produce 3 broods. So they have these broods over the course of the 7-day test. So usually when you first put your animal in the cup, the first couple of days will go by with no broods, but as the animal matures and gets bigger, it'll have its first brood on the 3rd day or 4th day, and it'll be about 4 animals, 4 neonates. And then a day or two later, they'll have their 2nd brood, and a day or two after that, they'll have their 3rd brood. So in some cases, you can terminate this test on the 6th day if all of these criteria have been met. And in some cases, you have to let it go to the 8th day for the criteria to be met. But it's pretty complex. And this is probably the most complex set of TAC. Brian mentioned reference toxicity tests. This is an internal laboratory QC step that we do where we measure usually either monthly or with every single batch of animals that we receive. We dose the animals with a particular dilution series of a particular chemical. Brian mentioned copper, but we can use salts like sodium chloride or potassium chloride. We use cadmium for some of our organisms. And what you want to do is you want to see if that organism responds the same way to that dilution series of a contaminant every time. We want a consistent response out of the organism. So if you measure, in January and your response as measured as an LC50 is way up here, and then you measure the next month and it's way down here and it's bouncing all over the place, that's not good. That shows that your organisms are variable over time. And even though you might be getting them from a supplier, the problem might be that the supplier's producing variable organisms because of conditions. It might be that because of Federal Express or UPS, the organisms are sitting on a hot runway somewhere, on their way to your laboratory. Or it might be because you're not very good at doing the toxicity test that you're getting variable data. But the idea is to demonstrate how tight your data are over time. So this is an actual control chart from our laboratory with Hyalella azteca. It's an acute test. It's only 96 hours. We only look at survival, and we dose them with cadmium. And then over time, we have, it bounces around a little bit. But the green line here in the middle is the mean response over time, the running mean. And then the dotted lines above and below are plus or minus 2 standard deviations. And this is sort of a standard way of looking at the performance of the organism over time. And if we're outside of that, like we're almost outside right here, but if we're ever outside of that, it doesn't mean that we've failed the test. It doesn't mean that we're going to repeat a test in the effluent world. It's not a de facto criterion for a test rejection. It just means that the organisms were either a little bit more sensitive that month or a little bit less sensitive that month, or that there was just variability from some other source. What I always see in our lab is what always seems to happen is somebody new will set up the reference toxicant test. And they'll make their dilutions
of the metal. They'll fill up all of these beakers or vials with water. We'll put our animals in, and at the end of the reference toxicant test, nothing's died. And you wonder, and then you'll ask, well, were you measuring in microliters or milliliters? It's just some simple laboratory question, and and there's usually some mistake that was made along the way that shows that all of a sudden, you have an EC50 that's way up here. The animals weren't very sensitive that month, and it's usually because of a mistake along the way. So yeah, so this is mostly an internal thing. And one more thing I wanted to point out with this is when you're looking at like the SWAMP database, the databases like SWAMP and SEDEN don't contain these type of data. So again, this is something that there might be a question about laboratory performance when if you're looking at an ambient data set, you might want to question what happened in the lab at a particular set of data was produced. But this kind of data is not included within those databases, but can be requested. Again, laboratories have these on record as part of their certification. When you get certified, you have to demonstrate that you can do the test, and this is the way that happens. We do a bunch of reference toxicant tests of a particular protocol, and that gets submitted.
Another thing that most good laboratories do is they monitor their performance in terms of other laboratories in the country. And this is a table from the current TST technical document. The TST is the test for significant toxicity. And they used this table to demonstrate it's a summary of mean controlled germination in a kelp test, and it's a comparison of a number of different labs from across the country. It's 135 different chronic kelp tests, and so there's percentiles of the laboratory performance, and so in this test you need to have 75% controlled germination to have a valid test. So if you recall, these are little spores that you're putting into the water that you're testing, and over 48 hours, those spores are going to germinate. And so you can tell a germinated spore from an ungerminated spore by the way it looks. I mean, the germinated spore has a little germ tube poking out of the side of it. They're like little balls and when they germinate, they look like little barbells, like an old-fashioned cartoon barbell. So you have to have at least 75% controlled germination, and so the lowest number here, this is measured as a proportion, so that's 78. And so most of the labs can hit 78, but the 95th percentile labs are the ones that are hitting 97% controlled germination. So this, you want to basically be, as a laboratory, you want to be further down this list. You want to be the highest performing lab that you can be. And it's good to be able to compare your lab performance to the labs across the country that have done these tests. Well, in this case, the kelp test, it's probably the labs on the West Coast that have done these tests. And so, full disclosure, Granite Canyon is actually, I think even though we developed this test, we're at like the 25th percentile. So our controls are usually in the 80s, like the 85 to 90 range. And so we're down here. So there's a lot of labs that do tons and tons of these tests that are higher up in the percentile range than we are. And so Brian's right, and the point he makes is very good. It can be your organism source that might be a cause of your variability, as opposed to anything you're doing in the lab, like how clean your glassware is, or whether or not your technicians are trained. There's a lot of different sources of variability. But it's good to have the level of variability pointed out to you so you can try to reduce it. In reviewing a toxicity test report, the first and foremost, we should make sure that all the TAC have been met, the test acceptability criteria. Otherwise, the test is invalid and must be repeated. I know with effluent samples that are, data that are going to go into CWICs, you have to report the data from the failure as well as the repeat test that passed. So a failure can be reported or should be reported in that
in that area. But that's not always the case for something like the swamp database or seed. That's first and foremost, but then on down the line, there's sample handling, test conditions, the water quality measurements, things like dissolved oxygen and ammonia, the performance of the reference toxicant test. You asked if that should be included in a report. I think it should, but it's because it's good for you to see how variable the lab is over time. And then looking for variability, looking at that concentration response relationship. If it's a multiple concentration test, you want to make sure it has the right kind of dose response relationship. Look at that a little bit in statistics. And then lastly, reviewing the permit and making sure all the actual permit requirements have been met in order to consider it valid. QA/QC is the responsibility of the lab and the permittee. Sometimes those are the same thing, but it's basically their responsibility to produce good data. The data quality can be impacted by a lot of things. Test conditions, test acceptability, and test review steps, all method required versus recommended. And then the things that we think are most important QA components are the reference toxicant tests to evaluate organism health and performance. And then that table I showed with tracking control performance, I think that's important too for a laboratory to do. And lastly, making sure the water quality measurements are within acceptable